I'll start with a review of acid-base stuff. It's really last semester stuff. Start by saying first, in some sense, hydrogen, helium, lithium, beryllium, whatever. The periodic table, there's almost like there really should be one more that's even more fundamental than hydrogen. So I'll say this. Helium is, how many protons are in helium? One? Nope, two. It's at the very top right of the periodic table. So proton, proton, and for the neutral one, you've got electron and an electron, and that's neutral. But truthfully, there are some neutrons, and you can have one helium that has that many neutrons in it too, and some helium will have one. But and that's isotopes. But we really only talk about that very briefly at the beginning of 1211. Neutrons. But if we go to hydrogen, the vast majority of hydrogen in the universe is just one proton and one electron and no neutrons. If you strip away the electron, it's still something very different than all the other atoms. It's just a proton. It's literally just that subatomic particle, the proton. Acid-base is all about the proton. And we usually go H+ to indicate a proton. It's really not a hydrogen, it's a proton. I'll mess up and call it hydrogen now and then. But it's kind of like, 3/4 of the Earth is covered with water. Water's everywhere at the basis of life, and protons show up in water just kind of everywhere. So the protons are so prevalent that it's almost like there really ought to be just kind of one more special thing here, the stripped hydrogen that's just a proton, because it's so ubiquitous around the Earth, anywhere else really. And plasma is out in space. Okay, so acid-base. You can split things down into strong acids, base. Strong acids, here's an example. HCl is a strong acid. If you put HCl in water, I'm going to say aqueous. And for the water, I'm going to say L for liquid. Draw an arrow, and you get these are aqueous. If it's charged and it's in water, it's going to be aqueous. And I want to mention here that here's a water molecule. Let's say I'm drawing this water molecule. You already know from your Lewis structure lesson from last semester, oxygen has these two lone pairs on it. Here's what happens to form this. Along comes the H+, which is really just a proton. It has no electrons to donate to the covalent bond. Both of these electrons turn into the bond that this H comes in and connects to. And we end up with a positive charge on the oxygen now. So that's where the positive charge comes from. And notice both this pair of electrons, this is true for oxygen and widely true for nitrogen as well, because it's got a pair of electrons. That proton comes along and attaches to that pair of electrons. So that's how this ends up forming. And this is a polyatomic ion. I gave out a chart of polyatomic ions last semester. Have I had a reason to give you all one this semester? It's just that chart of all the polyatomic ions. Nitrate, sulfate, and all that. This is called hydronium. Polyatomic ion. And that's just one of the monatomic ions. Okay, so That's what happens with a strong acid in water. Here's an example of a strong base. NaOH, I'm going to say aqueous, H2O, liquid, and you get I want to do this. I want to do it in the form they do it here. Okay, we'll just show us this as you put that in water. Sometimes you'll see this depicted the same way this is. Turns into H plus Cl minus. But this equation is just showing the role of the water explicitly. Because really this forms, not this. This does form, but this is what really forms when you do this in water. Okay, and now let me write. Here's a weak acid. Weak acid. And this H I'm drawing on this side is the one that comes off. H2O, aqueous. Get a little space here just so it doesn't matter. We're not even really going to be looking at strong acids and strong bases here. Get that plus H3O plus, this will be aqueous, and this will be aqueous. Okay. And the key here is this: when you do weak acids, you get this error, the double error, because it's weak because this acid doesn't really completely dissociate into the H plus and this ion completely. It only does a little bit, so there's an equilibrium. So this picks up where we are now. We were talking about equilibrium. We're going to talk about weak acids and weak bases and all the theory that goes with them based on equilibrium. So instead of just the arrow, it's the double arrow. And now we're just going to move on and just talk about weak acids and weak bases. I showed you this. That it's the H plus that comes along and takes one of those pairs. Let me draw this for you too, because it's kind of a ubiquitous weak acid. Let me draw it for you. Acetic acid looks like this. Oxygen up there, oxygen down here. Let me draw. I'm going to draw in the pairs down here. Hydrogen there. Okay. That's acetic acid. And here's what acetic acid does. When you put it in water, this comes off as a proton, as a bare proton. And it leaves behind both of these electrons. So you have that, and this is negative. You have 3 pairs here around the oxygen, and then that pair there, and this line is negative. So there's negative and positive. So it's very much like this oxygen, where the bare proton comes off and leaves behind both of those electrons that was in the bond. That's how this ends up charged positive. And this is, of course, negative, because it left its electron behind when it came off. That's acetic acid. You sometimes see it written. And then the ion is sometimes CH3O negative. But they stick the H up here on the end just to sort of indicate that it's an acid. So this polyatomic ion is what's being depicted here. C2H3O2. Just so you have a picture of what's going on. So you've got an equilibrium here, and I'll do a weak base. This NH3 is considered a base, and let me say, I guess we can keep that. This is considered an acid. This produced H+, which is what attacked the water and turned into hydronium. And this, that pair of electrons on nitrogen, so there's the dot structure for nitrogen. If you put hydrogens all on here, it's neutral, and you call that ammonia. You could call it nitrogen trihydride or something, but nitrogen trihydrogen or something, but everyone calls it ammonia. To turn into this, it steals a proton from water. So here you've got water. If I pull off this proton but leave behind that pair of electrons, here's the pair of electrons. And this ends up negative. That's what the OH polyatomic ion is, and then there's the H+. That H+ comes over here, attacks this pair, it gives you this, which is now overall positive. So OH negative, there's the H+, this is a positive hydronium, there's ammonia. So you can say, if you wanted a definition, you could say, if you have something that you put in the water and it produces H+ in the water, you could say, let's define that as an acid. And for base, you can say, I should say puts. So I've got something and I put it in water, and if the result of that is there's some OH in the water, then I can say that's the definition of a base. This is actually the Arrhenius definition of acid base. And it's a little bit limited. So Bronsted-Lowry came along, made a different definition. I kind of want to leave all these here. Hydronium. Here's the OH. H+, ammonium. This here too. Negative. H+ there. The Bronsted-Lowry, I'll say BL definition, is base is a proton acceptor. So that's why this is a base. And this is a better definition for weak acids and weak bases. EAD Lowry. my shorthand way of saying its definition. You think about an acid as a thing that gives an H plus away, and a base is a thing that accepts an H plus. Slightly different from this. So this produces, I think this is interesting. NH3 is kind of unique. There are other ones kind of similar, but let me put a strong base here. Let's do this. NaOH, this is the one I had before. If you look at this and I say, hey, this puts OH in the water, and you look at it and you go, yeah, I believe that. It's got an OH there. Of course it does. There's the OH. But if I say, I'm putting this in water and it produces OH, you'll look twice at it and go, wait a minute, where's the OH? It's kind of interesting that this is how ammonia works. It works by grabbing one of the water molecules, stealing its hydrogen, thereby turning it into an OH. It didn't bring the OH along with it. You know what I'm saying? Okay. So having said that, there's some things we can go through. Thinking of acids and bases as proton acceptors and proton donors. Instead, Lowry. This is L, this is AQ, this is AQ, this is AQ. Okay. Compare these two things and tell me what the difference is between these two. The difference between these two is this has the presence of the proton and this is missing the proton. This thing that gives up the proton is an acid. This thing, notice it's a double arrow, so going this way, this is behaving like an acid. Going this way, it's accepting a proton, because both of these reactions go either way. So in that sense, this is a base. When the only difference between the two is the presence or absence of the proton, they're called conjugates. Here's a base, its conjugate acid is this. Here's an acid, its conjugate base is this. What are you laughing at? Are you laughing? You're not? I'm not picking on you. I'm just like, is my fly open or something? The thing that keeps, is it just a look on your face? I'm like, do I have a booger hanging on my neck? Okay, that's cool. If my fly's open, tell me though. I swear he's grinning every time I look at him. Okay, look at these two. What's the difference here? This one and this one.
Positive.
It is that, but there's something that I just mentioned here. They are conjugates. The difference between this one and this one is the presence of the proton. So these are also acid-base conjugates. So which one's the acid and which one's the base? Which one is this? This one's the acid because going this way, it loses its protons. The one that gives up the proton is the acid. This is the base, and those two are conjugates. And that shouldn't be a surprise because we kind of have this acid-base relationship here, and then we have this reverse acid-base relationship here. So conjugates. You with me? Okay. On this page, I forgot to say this one again. Okay, do you see the conjugate acids and bases here? By the way, this is ammonia, and this is ammonium. So these two are conjugates, these two are conjugates. The only difference here and here is the presence or absence of that proton. You see? The only difference here and here is the presence or absence of one proton, a proton. So this would be acid, and this is a base. This is an acid. No, this is seven. Yeah, that's giving up. So acid gives up its proton to become this. So this and this are conjugate acid bases. So you can break down any of these weak acid, weak base equilibriums into the conjugate acids, conjugate bases. So half on my PowerPoint. I did upload it. You guys see the PowerPoint? Did I upload it? So I'm on the page where it's got number 3 there, into the chapter problems or what I've got there. So this is saying, basically this is saying, show these things behaving as an acid. So show this behaving as an acid. And all that means is this. This behaving like an acid, well, it's going to give up a proton. So there's the proton popping off, and here's its conjugate base. Strong acid, HCl. This one behaving like an acid. In this case, never mind, these are, I've kind of done this one. So make NH3 act like an acid. What are you going to do? We're not going to turn it into NH4. That's it behaving like a base. What we have to do is rip off one of its hydrogens. Now it's NH2. But you can't tell what the charge is on NH2, right? If it's neutral here and it comes apart into a positive side, then this has to be a negative. There's a rule, I probably haven't mentioned it yet, that the charges on both sides have to balance. So on this side there's a total of 1 plus charge. On this side there's a total of 1 plus charge. That's just to double check that everything's done correctly. Here there's an absence of charge, and here's 1 positive and 1 negative that cancel each other out. So charge is balanced here too. And this one, charge is balanced too. You got a plus there, a negative there, they cancel each other. No charge, total charge here, no total charge here. Technically those charges do exist, but that's just kind of a bookkeeping thing you can do. Okay. So this was act like an acid. So make that act like an acid, make that act like an acid, make that act like an acid. And the next question is, make these act like a base. Act like a base. H2O. That's 2 minus. So these have to accept the proton. you accept the proton, you accept the proton. Which gives us H2O, NH4 plus ammonium, HCN. If you put CNH, I suppose I couldn't blame you, but this is an acid, and when it's an acid, we almost always put it on the left. I added this H to S. Kind of bookkeeping wise, what's the total charge over here?
-1.
Yes. You got a +1 and a -2, you end up at -1, so you need a total of -1 over here. So when I do this, I make the SH over here, it's going to be negative. Bear with me. HPO4, keep my neck sticking. Of course, if you add an H there, HPO4 is positive. Yeah, that's positive. What's not? It's negative. -1. So we'll have H3PO4 here, and that's -1, +1, so this should be balanced at 0. What I wanted to show you is, I'll go on and do some conjugates. But H3PO4 can come apart as H plus and H2PO4 minus, and then H2PO4 minus can come apart some more into H plus HPO4 2 minus. And then I can still take one more positive charge off of there. HPO4 2 minus can become H plus PO4 3 minus. All of these were on the polyatomic ion chart from my semester.
What made you decide to put the SH? What made you decide to put the H behind the S versus in front?
Exactly why we do this. This isn't a typical acid, but this is. In typical acids, we tend to write it on the left side, except for acetic acid. Just structurally, we end up writing it on the right side. There is a rule related to electronegativity, but don't worry about it. I give you A, B, C, D, and E on tests, so think that way.
On the lower right, was that for like reactions of it like for acid or the base? Because they're like losing
If this were behaving as an acid, it would do this. But this could further continue to act as an acid and pop off another one. And then this could continue and pop off another one. It's called a triprotic acid because it actually gives up 3 protons for every one of them that exists. But I just wanted to point out that these are the polyatomic ions you've seen before. And anyway, and this is just like, this is kind of the reverse of one of these. I mean, you could think of it going this way. This acting as a base to become this, and then this acting as a base to become this, and then this acting as a base one more time to become this. Which way you would shift equilibrium is kind of where we're going to make it go one way or the other. But let's do, my next page is about conjugates. So if you were given a reaction, what is it? Okay. OH. This is probably just belaboring the point, but how would you take these and make them act like a base? Meaning, actually the question is, give the conjugate acid of these bases. So this one you add an H plus, you get H2O. This one you add an H plus, you get H3O plus. This one you add an H plus, you get H2CO3. This is bicarbonate. I could do this, rip off a hydrogen off of this. So that's carbonate, this is bicarbonate. Those were both on the polyatomic ion list. Add a proton here. Add a proton here, H2SO4. If I popped another one of these off, I could have H plus, SO4 2 minus, that's sulfate, that's on the polyatomic ion list. So the polyatomic ions just show up over and over here. Adding a hydrogen to this, I would call it H3O2 plus. Add a hydrogen here. This is sometimes SH2 or H2S, depending on context, but don't worry about the order there. And this one would be H6 into 2 plus. This will be 2 plus. Maybe I should be writing the hydrogen. Plus H plus H plus H plus. So you're going to end up with 2 positive charges here. Here the positive and negative go to neutral. Here you're going to end up with a positive charge. Here it's going to end up neutral. Here it ends up one more negative to positive. Now it's bugging me. So here's all of these behaving as a base. I'm able to add an H plus to them. Now, so these questions that are on here, these are the types of questions I'm going to eventually get on D2L. I got a little bit of equilibrium from last chapter into D2L, but I have to go edit them and make sure they're correct. I'll have more of those later this afternoon. This. So if you were given this, these are all strong acid-base reactions. Okay, so the question is, can you identify the acid-base conjugates? It's not hard, right? NO3 by itself, if this just had a hydrogen on it, a proton on it, it would be this. Acid-base conjugates, and these are acid-base conjugates. These two are the conjugates. Those two are the conjugates. Is it the acid or the base conjugate? Base conjugate, acid conjugate. HCN and CN, so that's the base and that's the acid. HSO4 and H2SO4, those are the acid-base conjugates. Acid-base conjugates. Okay, these that I was showing you, the most obvious examples of something called amphoteric, or amphoprotic. Means it's something that can behave as an acid or a base. Obvious example that you've seen already. Let's see here. I should have H plus H2O makes H3O, but H2O can also lose an H. So this, it can behave as a base to become this, and it can behave as an acid to become this. That's what amphoprotic or amphoteric means. It can accept a proton, or it can give up a proton. Meaning it can act like a base, or it can act like an acid. And that's kind of why I did these. These are the same way. This can go either way. It can lose another proton or it can gain one. Same here for this one. It can lose that proton, behaving like an acid, or it can gain another proton, behaving like a base. And that's why I like that. Yeah, I guess I'll do that, because that will too. Like I said over there. But I like minus, that's 2 minus. Need enough room. It's plus. I like the way I did it before. Okay, that's neutral. Two of these in this sequence are amphoteric. That one, that one. This one can become this, it can also go that way. This one can become this, and it can also go that way. Amphoteric. There's a question, example 14.3. They're doing this one. They're saying, show this behaving as an acid, and then show it behaving as a base. If I do this, am I showing acid behavior or base behavior? Is this showing acid behavior or base behavior?
Acid.
Yep. Over here, the SO4 is by itself without the H, so all that happened going here is an H was given up into the solution. and then behaving the other way. So that's this acting like a base, accepting a proton. So it's got another proton. Amphoteric. You okay with that? The next question is my favorite. It's showing H2PO4. We deal a lot with these. These are really net ionic equations. So this is correct. So 4. HSO4, and I did plus OH. That is accepting a proton. They showed. Whatever my answers were, they showed for the acid, they showed. Either way, it's behaving as an acid. I guess that makes no sense. Skip 13 if you're looking at this. Now I guess we can answer this. What we want to say. Question here is, which of these are amphoteric? So if I wrote these, 3, that's that one being amphipoteric. And then coming apart into H plus. Okay. This one can't do it. This one can't accept another proton because of what I showed you before here. The only reason ammonia can accept a proton is it's got a pair here to grab. But once you turn it into this, there's no more pairs of electrons to grab onto. So that can't behave as a base. It can't accept protons. This has no hydrogens to give up. Is gaining a hydrogen, I think there is such thing as, oh yeah, HBr, H accepting proton. That's accepting, that's accepting. Yeah. That's one of the strong acids. But this one can't go this way. This one can go this way. Get NH3. Part of this question is to show what it can do, but it can't go that way. It can't accept any more protons. This obviously doesn't have any protons on it, so it can't do this. But since that's 3 negative, I could put an H plus on there. You could do H plus to get that, but there's no way to strip one off of there. So it's these three that cannot go both ways, and these two are able to go both ways. Does that make sense? So I told you we're going back to equilibrium. I said we wouldn't use single arrows, but the dissociation, I guess you could use single arrows. They use single arrows. I think they weren't supposed to through all this part I was just doing. Okay, moving on to more about equilibrium. Kc and Kb. We call those equilibrium constants the last chapter. This chapter is literally the same concept. We have a new word. In some sense, I think it's the equilibrium constant is the general term, and these should probably have more specific terms. But the equilibrium constant for acid-base would go call it Ka, Kb, A for acid, B for base. But it's the same idea, it's the same equation, the same concepts. This book says I'm certain that in my past this was called dissociation. And I think anywhere else in the world you're going to see that. And maybe acid ionization constant is becoming ascendant. So maybe I'll just use acid ionization constant here, and this is okay, so I guess I will just use what the book says. But it's literally the equilibrium constant for a weak acid, equilibrium constant for a weak base. Meaning, let me do HCl plus H2O. And I guess I want to use a weak acid. Let me stick with acetic acid. CH3O2H. So that's acetic acid, the one I've depicted up there. Acetic acid plus O2. And then H3O plus CH3O2 negative. So this is just this without the proton. The proton is gone here. Okay, and let me fill in, we'll call that aqueous. We call that L for liquid. These will be aqueous because they're ions. Okay. All right, so the equation, it's products over reactants, and you do appropriate with the coefficients, but these are all 1. All right, so you would go Ka equals concentration of H3O plus. There's a 1 there, so I don't have to put the 1 up there. To the first power. Products go on top, just like last chapter. Now I'm going to go concentration CH3O2H, and then concentration of H2O, right here. Are you nodding?
I'm ready.
I'm doing this just so I can pick on you. So I've got the reactants down here, and then the other reactant is this one, and I'm going to write it right here, right? Because it's liquid. Last time I told you, and I wrote it right about here, if it's that, or if it's solid, you don't include them down here. Aqueous you include, and gases you include. Okay, so that's it. That's the expression for the equilibrium constant. Yeah, okay, it's the acid ionization constant. And it means acid ionization because this is ionizing. And the extent to which this ionizes is denoted in this number. The more it ionizes, the more it goes this way, the more this gets bigger, the bigger this is. So weak acids that ionize a lot have high Kas. If they don't ionize much, they have low Kas. Also, we use kind of a shorthand form where we take this, the CH3O2, that can be whatever with a proton on it for an acid. So we do this. We go, that's the acid, and this over here that's negative, we go, that's A negative, and now it's general for any acid. Whatever A is, minus, there's the A minus, A minus, H, A. You see what I'm saying? Here A is, yeah, just because most acids we put the H on this side. Maybe I should do it like that. As in HCl or something. H is the proton that comes off. The A is the Cl that's going to be negative over here. So in that case, it was, when I was doing it before with the acetic acid, A would have been C2H3O2 that. Yeah, and the H is just the H plus that goes on there. So anyway, this is kind of a general form. You see what I've done there? Just to make it general for any acid, that's how it's done. The higher this is, we say the stronger the acid. The more it dissociates into the H plus and the conjugate base, the stronger it is. So this is also a way of saying how strong is the acid. So of all these weak acids and weak bases, they have a number here, and you can compare their strength literally by which one has the higher number. Whichever one has the larger products up here. Okay, and there's a similar thing. Should I say the one for bases? kV for bases is the same thing. That. Let's see what we got. The one for bases, you would write, for the general equation for the base, we'll just go B plus H2O liquid, this is aqueous, some base. I'll do it as a weak base. There's that, and then the Kb expression is the same idea. So there's the base with the acid on it. Here's the OH. So there's the products. I'm going to leave this off again, and then we'll just have B on the bottom. Okay, general expressions. So having said that, acid ionization constant. Some more space. This is example 14.9. And we almost certainly did an equivalent one of this in the last chapter. But what if you had, talking about, of course I just erased it. Just so you know what we're talking about, acetic acid. Comes apart into that H plus. So that's where it pops off. Okay, acetic acid, and let's say concentration there's the acetic acid, molarity. That's literally what the brackets mean, the molarity. Or it almost always means molarity. There are other concentrations. That one's concentration, and this one's concentration. CO2 minus, and those are both. Question is, what is the acid ionization constant if these are all equilibrium? Equilibrium concentrations. And you just calculate it. So if I use this, the HA is this, CH3CO. Negative A is this, 00118. If that's their concentrations at equilibrium, if you crunch that out and get, I'll just trust that they did it right. There is an appendix that has all the Ka for all various acids and all the Kbs for all various acids. I will just give it to you in a problem when you need it to calculate something. In this case, we were calculating the Ka. In the back of the book, we had 1.2. But anyway, I'm sure we did one like this for the equilibrium chapter. Just before you're given the concentrations at equilibrium, and you're asked to come up with the equilibrium constant. That's literally what we just did. There is a check your learning, for example, 14.9. Maybe you want to practice that. So there's Ka values, there's Kb values. All right, I have to take kind of an odd tangent off of this and talk about the autoionization of water. Auto meaning does it itself. That's 14.9. What I'm saying is, water will actually do this. And it is an equilibrium. So if you put pure water, pure water, and you just set it to meter, it doesn't stay all water. It actually does this. It auto-ionizes just a little bit. Which is odd. It only does it to a very tiny amount. But that actually exists in any fresh batch of water. There's a tiny amount of this ionization that goes on. And it is tiny. First, let's do this. This is called, so add this to the equilibrium constant names. Kw is the autoionization constant for water. It can also be called the ion product constant. But don't let all the fancy naming throw you off. It's still that same exact idea of equilibrium. I mean, if I put an equal sign here and said, okay, let's put these expression together. What's the expression for this? What goes on top? So I'm going to put concentrations for these over here. Concentration OH negative. And what goes on the bottom? Nothing. L, so that's it. That's what the ionization water calculation is. It's just that. It is very small. This would have been the numerator, but it represents the products. It is very small. Most of the water sits there like this. You'll also notice, you might see this sometimes written, because that's two H2Os. That's more typical of what we do. They were just being explicit, so they gave it to you like that. This is known, and it changes with temperature. So at 25 degrees C, it's known to be, and this is sort of standard ring temperature, it's 1 times 10 to the negative 14. Like I said, it's very, very small. Only a very, very small amount of this forms. All right. At 80 degrees, 80 degrees C, the constant is so this is only true at room temperature. That's the constant at 80 degrees C. So I have a question for you. is this process endothermic or exothermic? This goes back to what we covered last chapter. What'd you say? It is endothermic, and it actually says it right here. Did you read it, or did you logic your way through it? So how did you? You just took it 50-50? Okay, fair enough. For this to get bigger, for the KW to get bigger, let me be a little more clear. KW at 25 degrees C, KW at 80 degrees C is 2.4 times 10 to the negative 13. So this is a larger number than this, right? 10 to the negative 13 compared to 10 to the negative 14. Erase this. Erase this. Either the heat, so for this to go up, yeah, I knew I should have erased that. Right up here. If KW equals concentration of this, concentration of OH, for this to go up, that means these are increasing. That means we're going this way. Right? You follow that? This is the type of logic for these two chapters. For this to be increasing, which it does from here to here, 25 to 80 degrees C, if this is increasing, that means these are increasing, which means these are increasing, which means it's going this way. Right? Nod? Okay. So increasing temperature makes it go this way. Either I would write heat over here or heat over here, but I say when I'm putting heat in, increasing temperature, and it goes that way, that means heat had to be over here. When heat comes out, and you can feel heat, is that endothermic or exothermic? That's exothermic. So this is endothermic. Endothermic is where you put heat in like an ingredient. Exothermic is like a product that comes out. So this is an endothermic process. This process is an endothermic process. As evidenced by, you increase the temperature, you increase the KW value. Because that means this increases, that means you were going this way, and that's what increases the KW value. Here's a question for you. Example 14.1. I guess that was right at the beginning of the chapter. I just felt like it's an odd way to start the chapter. What is the concentration of given that this is the KW value at 25 degrees C, you can figure this out. Those are X. You've got plus H minus over. No, it's not there. X squared, yeah. All right, if you started out with none of this in just water and you let it go, that tells you that for every, I guess you have to say for every pair of water molecules that do this, you'll get one of these and for one of these. And then another pair, then you get another one of these and another one of these. What I'm saying is these are equal to each other. The concentration are equal to each other. They balance each other perfectly. See what I'm saying? I'm saying it's necessarily true for pure water. Those are necessarily equal to each other. If you started with no ionization water and you just froze time and you had some water, and then you went, okay, now I'm going to let time go and let it ionize. For every one of these that shows up, one of these is going to show up. They happen like there's a couple of pairs. See what I'm saying? So they're necessarily equal to each other. So all I'm saying is, if you want to know the equilibrium concentrations of either one of them, you're just solving that. You're solving, and to solve out, you would do a square root of kW equals x. So you just need to find the square root of this. Do you know the square root of that?
It's half of it.
Huh?
Is it half of it?
Square roots aren't half. Well, it's not half. It might look like it's half because the square root is. That's only because you add exponents. This is what x will be. The square root of this is 1 times 10 to the negative 7. Because if you multiply 1 times 10 to the negative 7 times 10, 1 times 10 to the negative 7, you get 1 times 10 to the negative 14. And the check you're learning for this example is, okay, what is it at 80 degrees? It's the same thing, you're just looking for a square root. It ends up being 10 to the negative 7 again. So 4.9, 4.9. I just felt like double checking it to be weird about it. The square of this, so 4.9 times 4.9 is right. I'm not getting the same thing they did.
Just the square root.
Oh, I bet what I should do is take the square root of 2.4. Square root equals
It worked on my calculator.
mine gave me 1.54. I must have done something wrong. 2.4. Oh, I guess I have to do it in scientific notation. Oh, I see what I need to do. If I'm going to do it, I don't have the fancy calculator. 10 to the negative 13. 10 to the negative 12. So now it's 0.24 square root 0.4898. I don't know why I'm wasting our time on this. I'm just being weird. 10 to the negative 6. Two significant figures, so I need to keep 2 here. 6. And then if I make it 4.9, it's 10 to the negative 7. So anyway, I don't know why I felt like double checking. I'm the one that makes mistakes. At least this semester, good Lord. It's usually me pointing out the book making mistakes. I think I'm all high and mighty when I do that, but man, this semester, could be humble. All right, so that, and there is one more thing. What's the one more thing? Yeah. Okay, that KW value, and we'll pretty much, I mean, I'll give you any values you need. You don't have to memorize them. KW, and I'll just remind us, this is at 25 degrees C, 1.0 times 10 to the negative 14. I mentioned that there are Ka values and Kb values. And any acid will have its Ka value. Its conjugate base will have its Kb value, and those are related to each other. I wanted to do this derivation. I guess I'll do it. Now, I've got more questions here, so let's just, I don't think the derivation is going to mean much, but the relationship is Ka times Kb equals Kw. So that equation, I don't mind giving it to you on a test, but this times this. So what you can do is take something that's, let's use their example. I'm sure the next one's an example. This is so this behaving as a base will have a Kb value. Nitrous acid. It said the conjugate acid, but this would be the conjugate acid. HNO2. All right, and then they give us this shit. I would give you. They wait till the solution to say this, but they would have had to have given you Kb equals. Kb is given its. Yeah, in another section, it must have mentioned this. So there's the Kb value, and you just solve for it. To get the Ka value, it's Ka equals Kw divided by Kb. Divide both sides by Kb. Right? So we're just going. There's the Kw. Kb is 2.17 times 10 to the negative 11. 10 to the negative 11, that's right. If it was me, I would just do this part first. And then 10 to the negative 14. I would just go 1 divided by 2.17. Calculator said 0.4608. That's actually 1.0. So two significant figures. The next digit is a 0, so I'm going to keep that. And then 10 to the negative 14. Times 10 to the 11, so I'll bring this up to the top, which makes that positive. So negative 14 plus 11 gives me 10 to the negative 3. And then if I move the decimal to make it standard scientific notation, that's what they should have. So if they have 4.6 times 10 to the negative 4. There's a check you're learning there you can try. And then question 35 had one that's just like that. What is the ionization constant at 25 degrees C for this weak acid? The conjugate acid of the weak base, blah, blah, blah. But you can practice those before I get any questions on D2L. I think we have just enough time to do these. This next set of questions, this is from the back of the book, number 48. So I would do this. It says, which of the following increase the percent or the amount of NH3 that is converted to ammonium ion in water? I would give you on a test just to make it clear what I'm asking, and I don't even like the way they phrased this. It's saying, which one of these things that I'm going to add is going to increase the amount of this? It's phrased as, which of the following will increase the percent of NH3? And if you lose your train of thought, you'll think it's talking about this. It's saying increases the conversion of NH3 to NH4. It's really saying which one of these will increase this, the amount of that. Go back to last week where I'd say change this concentration, it goes this way, Le Chatelier's principle. Or change the pressure, or change the temperature, which way does it shift? We're kind of saying, what can we do to shift this way? Oh, I should have this. I'll forget that double arrow a lot. If we add NaOH. But think like this. If you add NaOH, what's going to happen is you're going to get Na plus OH minus. Forget about the Na. That's kind of a spectator here. We're going to increase the concentration of OH if we put NaOH in there. You see what I mean? So if I increase the amount of OH, what's that going to do to NH4 based on the way we talked about this last time?
Decreasing slightly, or is it increasing?
Well, it doesn't matter where you increase it. So then it's going to go back to equilibrium. What has that done once it goes back to equilibrium to the amount of NH4 that's there? If I put more of this in, we'll flow that way. And we will end up with a tiny bit more of this than we started with, but we're going to end up with less of this because you have to use up some of this to go that way. This is what I increased the amount of. I didn't touch this. So if I increase this, it goes that way with Chatelier's principle. So we'll get less of it if we add NaOH. Add HCl. And think now we're going to have H plus and Cl minus, but kind of forget about Cl. It's sort of a spectator. It's not doing anything. If you put some H plus in there, you're going to get, this is a weak base and this is a strong base. So the H is going to combine with the OH to make water. So it's going to make it go that way. H4Cl. I guess I have to talk about strength of acids and strength of bases before we can do these. HCl, the H plus ends up going here and making more NH4. But let me save us fuller discussion of that. The next one was add this is a polyatomic ion, NH4. So NH4 is plus and Cl minus. So that's just an ionic compound. If you put that in water, you get Cl and you get NH4 plus. So if you put that in there, you increase it. Did I not put the answers for this? I suppose I'll trust them. let's save that one. We'll see about the questions like this one. I think the last one we go over are questions. So I had 4 like this, but let's come back to that. So we'll don't waste our time having to figure something out. Okay, what is KA? This is number 54. Might be fading on you guys. Ka equals, for this reaction, and we're calculating Kb because it's a weak base, aqueous, and then we're going to have NH4 aqueous minus, and then that means Kb is okay, right? That's the formula for this. I'm leaving this out because it's got L with it. And then they give you this concentration. And they give you this concentration. Oh. And if I gave you this question, I would give you Kb. Oh no, wait a minute. So this concentration is going to be the same as this concentration. So those two are the same. So that's what they give you. They give you all 3 of those and you can calculate B. Actually, they give you this and this, but you can infer that these 2 are going to be equal to each other, just like we did before. And I'll just stop there. So if you crunch the numbers, you can calculate Ka. I guess I didn't stick the answers on with this one, but it's in the book. So something you can practice before I get them on D2O. I'll get the stuff from the last chapter on D2O before I get these on. So if you just want something to cover, look at what was in here. The answers are in the book and see if you're okay with it.